Hello, my name is Dmitry Soshnikov. Welcome to Functional Programming course. And we will continue now talking about trees, and we will try to think how can we make function that process trees to be tail recursive using the notion of continuations. So the idea of tail recursion is that we can convert a recursion into iteration by arranging function in such a way that the functional call is the last one that happens during function execution. And that cannot be easily done with functions that deal with trees, because when we deal with trees, we typically have nonlinear recursion, which means that we have two function calls inside of the function body. And normally when we implement this in the traditional programming language, it is implemented by using stack. So whenever we have a function call, whether it's recursive function call or normal function call, the return address is placed on stack together with arguments, and the function is called. Then when function stops executing, it returns back to that return address. So in tail recursion, because the function call is the last one, we don't need to remember the return address. We just continue the execution from the same function body from the beginning. But another way to arrange that, instead of using stack, we can use a technique called continuation by manually constructing the structure which will hold the functions that we need to execute later on. So let's see how this can be done and what are continuations in general. And let's start with general understanding of the continuation method. So normally in functional programming, we have functions which process information. So let's say we can have function +1, which takes an argument, adds 1, and returns the result. And then we would have some other function which will call this function and then arrange the execution around it. But we can also try to structure the functional program in a different way by providing a function that should execute after the one that we are defining. So, for example, we can have this function +1, which will take the initial argument x, and then it will take the function f that should be executed afterwards. And what it will do, it will call f on x +1. Then if I want to multiply something by 2, again, I will create this function as the function which takes an argument, and then it takes the continuation f and calculates f of x times 2. Now, if I want to calculate 2x plus 1, what I would do, I would first call +1, and then as a continuation, I would pass the function which takes x and calls times 2. So that is more complicated code. I mean, why would anyone want to write something like that? Well, because it allows us to explicitly define the order of execution. And in a lazy functional programming language, if we need to specifically say in which order we should execute, that is the good way to do it. And we will see later on that on top of continuations, we can create some more higher level abstractions like monads that will help us to do that more clearly in the code of our functional program. But right now, why do we need continuations right now? Because continuations is another way to deal with recursion and to convert non-recursive functions to tail recursion. And let's start with a very simple example. Let's start with lists. So suppose I have the simple function to calculate the length of a list, and I want to convert it to tail recursion. So what normally I would do, I would use accumulator. I would put integer accumulator here. I would return accumulator. And here I would call accumulator +1. And I will start with 0. So that would be essentially equivalent to the code before, but tail recursive. How can I use continuations instead of accumulator? So in this case, accumulator would not be an integer. It would be a function which I need to call afterwards to get the result. So how it would be constructed? So instead of adding 1 to accumulator, I would say, okay, accumulator is a function, and in order to add one more element in the list, what I need to do, I need to compose it with a function which adds 1 to a value. And then when I have the arrive to the end of the list, I will just call this continuation on the value of 0. So it would be ec of 0. And instead of the initial value 0, what I will do, I would pass here the identity function, right? So that code is equivalent to the previous one, so it would also return 10. But instead of the number, instead of accumulator, I'm using the functional continuation. And what I'm essentially doing, I'm building the chain of functions which will compute the result when executed. And right now it's not obvious, I mean, why would I want that? Because in terms of like memory, that's probably more difficult to build this. It takes more memory to build this chain of functions than to store just a number. But as we will see in the example with trees, those functions which we compose can have very complicated structure inside. So going back to the slides, of course, if I want to create this function in a nice way, I would make it an inner function, and that would be another way to define tail recursion. So now let's think about the simpler function which calculates the size of a tree. Normally, to calculate the size of a tree, I would use something like this, right? So it would be a non-binary, non-linear recursion, and each time I would compute 1 plus size of the left subtree plus size of the right subtree. So with continuations, I would do something similar to lists. I would pass here the continuation, the function which I would need to call to calculate the size of the tree. And when I arrive at the end of the tree, when I arrive to the empty tree, I will return continuation of 0 in the same way as I did when I calculated the length of the list. Now, what would I do if I have the node with left and right subtree? Well, what I would do, I would call the same recursive function. I would call it recursively. And I will pass the continuation, but continuation would be a little bit more complicated because I don't need just to increase the number by 1, but I need to increase it by the number of elements in the left subtree. So I will pass here the function, and because it's a continuation, this function would have an argument, right? So I would start with the previous argument. That would be some value that is passed to me from the previous call. And then what I need to do, I need also to get the number of elements in the right subtree. So here I would have another functional call which calculates the number of elements in the right subtree. And it would also take the continuation. So this continuation would give me some number of x2. And then I would need to add this x1 and x2 and also add 1 for the current node, right? So I will call the continuation which was passed to me with the argument x1 plus x2 plus 1. That is a little bit, well, maybe not immediately clear, but if you think about it, that is quite natural. So what continuation does, it is a function which does something to the argument, right? So when I call this for the left subtree, it's kind of I'm getting the number of elements in the variable x1. Then with the right subtree, I'm getting a number of elements in x2, and then I return x1 plus x2 plus 1. So overall, the logic is quite clear still, but the way it is executed is quite complicated. And you can say, why is that tail recursion? Because that is not obvious that it is a tail recursion. But if you look at the function call, what happens here, once I encounter the node, I immediately call the function on the left subtree, and I pass it some constructed in memory delayed call to the right subtree. So I'm not calling the right subtree immediately, but it is not delayed on stack. It is delayed explicitly as the parameter of the function. And that is better because, first of all, the stack is not exhausted because all those functional calls are constructed on heap and not on stack. Also, this call to the right subtree is not expanded immediately. It is expanded only when it comes to it. When it comes, when it starts executing, when I call continuation of 0. So we end up with a tail recursion, but the delayed execution, the recursion which we need to execute, is stored explicitly as the parameter of the function call. So this is called continuation style of converting recursive functions to tail recursion. You can simplify that even further, because you can note that I have left and right subtree, and I can kind of use accumulator as well. So I can combine accumulator and tail recursion, accumulator and continuation, and use continuation only when I compute something along only one direction. So what I can do here, I am passing here the accumulator and the continuation, and t is my tree. So what do? If I encounter the end of the tree, I call the continuation, but not on 0, but on my accumulated value up to now. Then when I encounter a node, what I do, first of all I pass 1 plus accumulator, so I go along and I immediately take account for the current element. Then I pass the left subtree, and then the way I construct the continuation is to call size prime on the right subtree with this continuation. So that kind of simplifies it, because in my continuation I have only one delayed recursive call, right? This is the only one delayed recursive call instead of 2. Here I had one delayed recursive call for the right subtree, and that simplifies the computations quite a bit. So the takeaway here is that you can still write the functions that process trees in a tail recursive manner, which means that you can process really large trees without exhausting stack. It doesn't mean to say that the computation would be simple. Of course, they would require a lot of steps, the same number of steps as the recursive version, but they would just not exhaust stack. So in general, in terms of trees, what we can say that trees are quite different. And when you are dealing with syntax tree, or when you are dealing with binary search tree, those two are very different. For example, abstract syntax tree is normally small because you will not process the huge program. But the search tree can be really big. If you want to build the frequency dictionary of Wikipedia, you would have to really use a lot of memory. So you need different considerations when dealing with those. And that's why there is no standard library for trees in the F# standard library. And trees are often implemented by programmer according to his own problem, to his own specific problem. Most of these scenarios are abstract syntax trees and binary search trees, but in general trees there are also things like files, directory structures, processes, and threads inside the operating system, which are tree-like structures. So next time we'll talk about more specific functional data structures, and we will see how we can combine functional way of thinking with lists and trees to represent some more interesting abstractions, such as zippers, which would allow us to represent, for example, directories with current directory, or things like Turing machine ribbon with the current element efficiently in the functional program. So stay tuned for next lecture and have the great time learning functional programming.